PPT தெரியுதாமா?
Yes, sir.
Okay, fine. Right, we can start. So we were looking the air standard cycles in the last class. So we can continue. Right. So we are looking the air standard cycles. In the last class we discussed this. What about the Carnot engine? And what about Carnot cycle? Then for the IC engines we have a cycle. So these are the IC engines. Then we have the general principles of IC engines. Then the terminologies and terminologies for IC engines. Then we were seeing the auto cycles, and the PV diagram of auto cycle, realized auto cycle. It's only a problem, right? Right. Auto cycle have two isentropic process, then two constant volume process. Then to look at
cycle, right? So you know very well the Otto cycle has two isentropic process and two constant volume process, but in the case of diesel cycle, we have to replace a constant volume process with a constant pressure process. That will be the process here. So how can we achieve the diesel cycle? The fuel is injected into the combustion chamber very late in the combustion stroke. So you know what are the processes in the IC engines? So we have a compression, we have combustion, we have expansion, we have exhaust. Right. So we have four strokes here. So after the combustion, we will initiate a injector, right? So after the compression, we will initiate the spark plug to get a combustion, right? So here in diesel cycle, the fuel is injected into the combustion chamber very late. Okay, where in the case of Otto cycle, the fuel injector will be in between the compression stroke. But to achieve this diesel cycle, we have to inject the fuel in the late state of our compression state. Right. So due to ignition delay and the finite time required to inject the fuel, combustion lasted into expansion stroke. So here that constant volume process will lasted and we can get the expansion stroke. So this gives the pressure at the peak level when past TDC, you know, top top dead center, right? So the pressure at peak levels will give you the constant pressure process here, right? Then the combustion process is approximated as a constant pressure heat input and an air standard cycle. So here the combustion process is approximated. So this is the indicator diagram of CA engine for diesel cycle. And in the case of Otto cycle, so this will start here, right? So the gas will be here, but when in the case of diesel cycle, so the state will be here. So this is a indicator diagram of a CA engine for a diesel cycle. Then this will clearly clarify the diesel cycle. So this PV diagram will give you the diesel cycle, right? So this is the initial state. This point is the initial state. Then we can get the compression at the later of compression. We will initiate the ignition. We will initiate the ignition here to get this constant pressure process. Then this is the combustion stroke. Then after that we can get the expansion, that is isentropic expansion. Then again we get the exhaust. Then again this is the pressure, atmospheric pressure. Then we will open the inlet valve. Then we can take the intake stroke. Then again it comes to the initial state. Then again there is a cyclic process. Right. So this is the PV diagram of our SI engine. SI stands spark ignition. Right. So here we will provide the spark here. Right. So here we can compare the Otto cycle and a diesel cycle. So where in the case of gasoline engine, so we will compress. We will first get compress of air fuel mixture here. So in gasoline engine, we will compress the air fuel mixture, but in the case of diesel engine, we will compress only air. We will compress only air. Then we will inject the fuel here. Then in the case of Otto cycle, we will initiate the spark by the use of spark plug. Right. So in the case of Otto cycle, air fuel mixture gets compressed, then a spark is initiated by the use of spark plug to get combustion. Then in the case of diesel engine, air gets compressed, then fuel is injected to get the ignition, to get the expansion, right? So here we have to look this diesel engine that is used for diesel cycle. So in this process, as usual, we have first stroke is isentropic compression stroke, that is compression stroke. Then the second process is constant pressure heat addition. But in Otto cycle, we add the constant volume process, but here we have constant pressure heat addition. Then, as usual, the third process is isentropic expansion. Then the fourth process is constant volume heat rejection. Right, this you can compare the both of Otto cycle and the diesel cycle. So Otto cycle has two isentropic process and two constant volume process. And in the case of diesel cycle, we have two isentropic process and one constant pressure process and one constant volume process. Right. So we can imagine with the use of this PV diagram and TS diagram. So we can get this. So PV diagram. So this is the initial state. Then there is a isentropic compression. Then there is a constant pressure heat addition. So this Q in will give you heat addition in constant pressure process. Then this 3 to 4 is a isentropic expansion. Then this 4 to 1 will give you constant volume heat rejection. Q out. Right. So these are the processes in diesel cycles. Then we can see the TS diagram also. So for isentropic process, this is initial state. So for isentropic process, we can get the entropy constant. Then we can get the horizontal line, the vertical line with respect to entropy. Then we have a constant pressure process. Constant pressure heat addition. Then we have again isentropic process, entropy is constant. Then we have constant volume process. Just we can compare the constant pressure process and constant volume process here. So constant pressure process is we can compare these two lines. So this constant volume process is steeper than constant pressure process. This constant volume line will be very steeper than constant pressure process. Right. So this is the PV diagram and TS diagram of diesel cycles. Then we have compression ratio RV. So compression ratio in the sense the volume, the ratio of volumes, that is from highest volume to, so this volume is the maximum volume to minimum volume. Right. So compression ratio can be calculated by the maximum volume by minimum volume, that is V1 by V2 here. Then also we have cutoff ratio. This cutoff ratio is same like compression ratio, where in the case of diesel cycle, so we have cutoff ratio that is V3 by V2. So this one, V3 by V2. The compression ratio can be calculated by V1 by this V2. Then cutoff ratio can be calculated by this V3 divided by this V2. Right. Just don't get confused. There is a ratio between the volumes. That's it. Then, as usual, we know the formulas for the separate processes. So we have isentropic compression at the first state. Then we have this formula that you know already. Then for constant pressure process, you know the heat addition will be MCP into change in temperature, that is T3 minus T2. Then again we have isentropic expansion, the same formula. Then in the last we have a constant volume process, you know the formula for Q out, that is MCV delta T. So delta T here is T4 minus T1. Right, so here is CV, then here is C. So because that is constant pressure process, then here is constant volume process. Right. So So just to try to recall these formulas, then we can formula for efficiency. So here the thermal efficiency of diesel cycle can be calculated as usual by output by input, that is work output divided by heat supply. Then this W net will be Q out minus Q out Q in. So we can derive this equation finally as 1 minus Q out by Q in. Then we can apply the first law for the constant pressure process, the second process. So if you apply the first law, delta U is equal to Q minus W will become, so we can have the W by adding other W values and W at the constant pressure process, right? So we can neglect this other works in this process. Then the constant pressure work will be integration of P dV. Integration of P dV. So here P is constant. So we can take this P outside. Then finally you know this formula, right? So if you integrate the P dV ideal gas equation, if P is constant, you will get this equation. You will get this equation, that is W is equal to P to E into change in volume. P into change in volume. So here there is 2 to 3 to V2, so V3 minus V2. Then we can take the pressure as constant. So if you substitute this W value into the first law of thermodynamics, then we can get the Q net as delta U plus P into change in volume. Then we can substitute the Q net here. So Q net here is Q in. So we can have the final equation as the change in internal energy will be M into Cv into delta T. So this formula can be written as M into R into T3 minus T2. So already we discussed these derivations, so you can go through that. So here we have MCV T3 minus T2 plus MR T3 minus T2. So we can take T3 minus T2 as constant, then M also constant. Then we will get MCP. Yes, what is R? R is equal to Cp by Cv, right? Cp by Cv. So this R can be replaced by Cp by Cv. And finally we can get this equation. That is for diesel cycle, for the second process, isentropic, constant pressure process, the Q in will be MCP delta T. Right. So this is the derivation for Q in. So we can derive the Q out here. So at the constant volume process, the process in 2 to 1 constant volume process. So as usual, the first law of thermodynamics. Then the work done by the constant volume process. So here volume is constant. The integration of P dV. If volume is constant, the whole term will be 0. The whole term will be 0. So 0 plus 0, there is no work. There is no work in the constant volume process. And if you apply that in the first law of thermodynamics, we can get the Q in. Sorry, Q out. So Q out will be change in internal energy. So that is MCV delta T. Right. So Q out is MCV delta T. So this is the derivation for Q out. Just keep the formulas alone. Then we have the thermal efficiency of a diesel cycle as 1 minus Q out by Q in. So we know the value for Q out, and we know the values for Q in. Then if you substitute, finally we can get this equation as like this. Right, so that is 1 minus mCv delta T divided by mCv delta T. Then you know this for process 4 to 1, PV is equal to constant. From ideal gas law, we can derive this equation. PV by T is equal to constant. So PV equal to, that is constant of T, right? So M R T. So we can take this constant. So P V divided by T will be, this is right. T by Pt. So PV by T will be equal to constant. We can expand the process. So P4 V4 by V4 is equal to P1 V1 by T1 for the process of constant volume. So we know constant volume. So V4 is equal to V1 here. We can cancel this too. Then finally we can have the equation as P4 by T1 is equal to P4 by P1. Right. So also you know the isentropic process. For isentropic process, it is PV power n is equal to constant, that you know. So here n is K, that is 1.4 for ideal gas. Right. So they can the PV power K for the all the process. So we can write P1 V1 power K equal to P2 V2 power K equal to P3 V3 power K, like that. So here we have to compare the process 1 to 2 and 3 to 4, that we have isentropic process. So we can write the equation as P1 V1 power K equal to P2 V2 power K, and P4 V4 power K equal to P3 V3 power K. Right. So you know very well V1 is for volume, constant volume. V4 is equal to V1, and you know for a constant pressure process P3 is equal to P2. So if you substitute the values here in this equation, we can finally get this equation, that is P4 by T4 is equal to V3 by V2 power K. We know very well is V3 by V2 here is cutoff ratio. This V3 by V2 is cutoff ratio. Then we can write the equation as P4 by T4 is equal to RC power K. So RC stands cutoff ratio. Then you can substitute this P4 in your this. Yes. Right. So we substitute the P4 V4 value in the thermal efficiency, and finally we can get the thermal efficiency of a diesel cycle as this. Okay, 1 minus Qn will be 1 into Rc power K minus 1, then Rk minus 1 into K into Rc minus 1. Just we can substitute, then we can get this final equation of thermal efficiency. Right. So just remember the formula for thermal efficiency of diesel cycle as 1 minus 1 by R power K minus 1. So here R stands RB, compression ratio. Right. So here R stands RB, compression ratio power K minus 1. Then RC stands cutoff ratio. Cutoff ratio power K minus 1 divided by K into RC minus 1. Just remember this formula, that is for efficiency, thermal efficiency of diesel cycle. That's it. So we can compare the thermal efficiency of a diesel cycle with the compression ratios. If you increase the compression ratio, if you want to increase the compression ratio, you can get the increased thermal efficiency. Right. Then also we can compare the compression ratio with mean MEP, that is mean effective pressure. So if you want to get the increased mean effective pressure, we want to increase the compression ratio. So also heat supply in this process will be a matter to achieve the highest efficiency, also the highest mean effective factor. Right. So from this statement we can clear that. So in diesel engine, the fuel cut-off ratio depends on the output. Depend on the output. So if maximum, there will be maximum output. Right. So the cut-off ratio will be the factor here. So you can get the increased efficiency by increasing the cut-off ratio. Then you can go to the problem. So as usual, the same problem like auto cycle. But here the values for diesel cycle are given, and we know how the diesel cycle will be. Then what are the process involved in this diesel cycle? Then if you know the formula, you can get the unknown values. So here we want to calculate. Just go through the problem. An as standard diesel cycle has a compression ratio, that is R is given 20, and the cutoff ratio 2.5, also RC also given. The state at the beginning of compression is fixed by P is equal to 0.9 bar and T is equal to 300 Kelvin. So they gave P1 and T1. Then we have to calculate the thermal efficiency of the cycle. And the second, the maximum pressure T max, then the MEP, the mean effective pressure. So we have the values P1, T1, RB and RC. So RB in the sense V1 by V2 here, then that is 18 here. Then cutoff ratio RC will be V3 by V2 here, and that is given 2.5. So also we can compare the PV diagram of diesel cycle. So isentropic compression, then constant pressure heat addition, then isentropic expansion, then constant volume heat rejection. Right. So for the process 1 to 2, we have isentropic compression. So we know the formula. So here we can take the values for T and P. We can take the formula for T and V. So if you take, you will get the equation as T2 by T1 is equal to V1 by V2 power K minus 1. Right. So we know the value for V1 by V2. Then we know the value for T1. If you substitute, you can get this T2. Right. Just use your calculators. Then cross check the values. Then only you can get the practice. Right. So the V1 value is given. Then V1 by V2 value also given. So if you substitute for the process 1 to 2, you can get the effective value. So that will be 3.3 Kelvin. Then we can move for the process constant pressure process. So we know the formula, that is P2 is equal to P3. Then that P2 can be written as P2 by T2. Then we know T2 is equal to T3 here. We can substitute the equation as T3 equal to T2 into V3 by V2. Right. So we know the value of this V3 by V2. They given cutoff ratio. V3 by V2 equal to cutoff ratio. Then if we calculate the T2 value, it is 953.3 Kelvin. And if we substitute, we can get the T3 value. Right. The T3 value will be approximately 2383.3 Kelvin. Yes, you can cross check the value with the use of calculator. Then we can move for the next process. There is again isentropic expansion. So we know the formula again. It is V4 by V3 is equal to V1 by V2 into V2 by V3. Right. So if you substitute, you know the values, right? You know the value, that is compression ratio. Then this is inverse of cutoff ratio. This is the inverse of cutoff ratio V2 by V3. we can substitute. Then finally we can get the V4 by V3 volume ratio as 7.2. Then we can substitute here. So why we find this V3 V4 by V3, because we have the equation for isentropic expansion as T4 by T3 equal to V3 by V4 power k minus 1. So we want to find the V3 by V4. So for that we can use the compression ratio and cutoff ratio. If you multiply compression ratio with the inverse of cutoff ratio, we can able to derive V4 by V3, and that V4 by V3 can be used for the calculation of T4 by T3 equal to V3 by V4 power k minus 1. Then we know the value for this V3 by V4, then we calculate the value for V3, T3, that is 2383.3 Kelvin. So we can substitute. Then the unknown value T4 can be calculated. This T4 can be calculated. Then that value will be 1082 Kelvin. Then we have to move the next process. So I think we found our parameters. Right. So we know T1, V1. We found T2. We found V3, V3, V2, V3, V1, V2, V1 we know, V2 we know, V3 we know, then V4 also. Right. So we can, for the next process, it is the final process, isentropic heat rejection. Before that, we can calculate this QEL for the second process, also for QOut for the fourth process. But you know the formulas. So MCP, this changes. It is not CP, it is CP. So you know for functional volume process of the heat rejection, so we have MCV delta T. Right. So if we substitute the formula, then we know the values for T3 we found, T2 we found, T4 we found, T1 they given. So if you substitute, then get the QN as 1437.15 kJ per kilogram. Then we can found the QOut as 561 kJ per kilogram. Then if you substitute, you can get the work output. Its net work done with the system can be calculated by QN minus QOut. So if you subtract these two values, you can get the W net. So again, finally we want to find the thermal efficiency of diesel cycle. That you know, that is one W net by QN. So we calculated W net here. Then we know the QN value. We know the QN value. So if we substitute, we can get the thermal efficiency of this diesel cycle will be 60.93%. Right. So the first question we answered. In the second question, we have to calculate. We have to find the maximum pressure value. So if you compare the P2 value and P3 value, will be the maximum one. That will be 5148 kilopascal. That is your Pmax. Then also we want to calculate the MEP, mean effective pressure. The formula you know, that is W net by V1 into 1 minus 1 by R. 1 minus 1 by R. So we know the values W net we know, V1 we know, then R value we know. So if you substitute, we can get the MEP value as 969 kilopascal. So by this way we can calculate the problem for a diesel cycle. Right. So you have to remember, diesel cycle has 4 processes. First process is isentropic compression. Then second process is constant pressure heat addition. Then third process is isentropic expansion. Then fourth process is constant volume heat rejection. Right. So this is leaking process again. So the initial state and final state will be equal. So just keep in mind. So these are some supplementary problems. Over to you to solve in your home. Just try to solve the problems as a homework. Then we can move to the dual cycle. Right. So we know what is Otto cycle. Then we know what is diesel cycle. So we can look what is dual cycle. A fuel is injected earlier in the combustion stroke will give you this diesel cycle. Right. So we know after combustion we will initiate the fuel or we will initiate the spark. Right. So in the diesel cycle, if the fuel is injected earlier in the combustion stroke, we will get this dual cycle. So some of the combustion occurs almost at constant volume at a target chamber, similar to Otto cycle. So we can get the Otto cycle, diesel cycle, both together will give you the dual cycle. So the fuel is being injected at the target chamber, and the combustion of the fuel keeps the pressure high into the expansion stroke. Right. So the heat input process of a combustion is approximated by a real process of constant volume followed by constant pressure. So we can have the constant volume process followed by constant pressure process to achieve this dual cycle. So we can take this PV diagram of a indicator diagram of the dual cycle. So as usual, we can have the initial point here. So there will be a isentropic compression. So at this stage, so we will initiate the fuel injection. So this will give you the constant volume as well as constant pressure. Right. Then again we will have the isentropic expansion. Then we will bring back the initial stage. Then exhaust. Then intake. So the process will be same, but the fuel is injected at the mid of the combustion stroke. So we get the diesel cycle. So here we can get the PV diagram of real cycle. So from process 1 to 2, isentropic expansion. From 2 to X, we have constant volume process. Then X to 3, we have constant pressure process. Then 3 to 4, we have isentropic expansion. Then again, we have a constant volume process. Then exhaust, then intake. It will be initial state. These are the processes involved in the real cycle. Then also we can look the TS diagram. So you know, for isentropic process, entropy is constant from process 1 to 2. Then constant volume process. So constant volume process is steeper than constant pressure process. So the line will be very steeper. Then again constant pressure process. Then 3 to 4 isentropic process. Then again 4 to 1 the same constant volume process. So the PV diagram and TS diagram of real cycle will be like this. You can refer. And, you can get the finished PV diagram of this real cycle. Will be first stage will be isentropic expansion, then constant pressure heat addition. Also here also constant volume heat addition will be there, and in the process 3 to 4 constant pressure heat addition will be there. So there is 2 heat addition. If you want to calculate the net heat addition, you have to add both together. Then we have isentropic expansion, and finally we can have the constant volume heat rejection. We have only Q out, only Q out. We can remember that. Right. The real cycle gives a better approximation to a real engine. So this real cycle is an example for real engine. The heat addition process is partly done at the constant volume and partly at the constant pressure. So both together will give you the heat addition. Then from the PV diagram, so it looks like the heat addition process is a combination of both Otto cycle and diesel cycle. So this heat cycle can be derived from the Otto cycle, combination of Otto cycle and diesel cycle. And as usual, we can refer these processes. First process is isentropic compression. The second process is constant volume heat addition. And the third process is constant pressure heat addition. And the fourth process is isentropic expansion. Then the fifth process is constant volume heat rejection. Then if you derive the equation, finally we can get the equation, thermal efficiency of this dual cycle as 1 minus Rp Rc power k minus 1 divided by Rp minus 1 plus k Cp into Rc minus 1 into Rp power k minus 1, where Rc cutoff ratio, then Rp Rp here is pressure ratio. Rp here is pressure ratio. Then Rv compression ratio. Right. So this will be the thermal efficiency of a dual cycle. Then we can move to the problem for a dual cycle. Just go to the problem. The process will be same and the formulas will be same for all the processes. Then we have to look at the thermal efficiency of dual cycle in calculate. Right, just go through the problem. At the beginning of the compression process of an air standard cycle, dual cycle, with a compression ratio given, RV given, that is 80. Temperature is 300 Kelvin, T1 given, and the pressure is 1 bar, T1 given. The pressure ratio for the constant volume part of the heating process is 1.5. Pressure ratio RP given, T1 by T2 given, it is 1.5. Then the volume ratio for the constant pressure part of a heating process is 1.5. So they gave cutoff ratio. So here they state that the cutoff ratio as the volume ratio for the constant pressure part, right? So we have V4 by V3 is 1.2, right? So we have to determine the thermal efficiency and the MEP. Right, as usual, we can have the PV diagram of a dual cycle. So we know isentropic compression, then followed by constant volume heat addition, then followed by constant volume constant pressure heat addition, again isentropic expansion, then constant volume heat rejection. So we know the values V1 by V2 given, T1 given, T1 given, then T1 by V2 also given. So from that we can calculate T2. Then we know V3 by V4. So V4 by V3, that is 1.2. Then we can try to find the other states properties. Right. From process 1 to 2, there is isentropic compression. You know the same equation. So we have to compare the parameters T and B. If you compare, you can get the equation as T2 by T1 is equal to V1 by V2 power K minus 1. Same equation. Right. So we know the V1 by V2 value. Then if you substitute, we know the T1 value, and if you substitute, you can derive the, you can calculate the T2 value. That will be 953.3 Kelvin. So 0.4 times from K minus 1. So you know the K value is 1.4 minus 1 will give you this 0.4. Then finally we can get the T2 value as 953.3 Kelvin. Then for the second process, we have constant pressure heat addition, that the formulas. So T3 by T2 equal to V3 by T2. So we know the values T2, then they gave the values for V3 by V2, and if you substitute, you can calculate the T3 value. As 23 A3.3 km. Then again, we have a third process here is isentropic expansion. Again, we have the right. So we can have the equation as V4 by V3 is equal to V4 by V3 is equal to V3 by V4 power A minus 1. So this V3 by V4 they given. So we know we calculate the T3 value. If you substitute, you can get the T4 value as 1082.82 Kelvin. Then you can go with the process isentropic expansion. Then you can have this equation d5 by d4 equal to d4 by d5 power a minus 1. Then you want to calculate d5, then we have the value for d4 and we have the values for this. We don't have this value d4 by d5, so to get that you can write the equation as d4 by d3 into d3 by V3. So just we have multiplied V3 in the top and bottom. Then we know these values. We know these values. Then if you substitute, we can get the value of T5. So this is the T5. So the value will be 584.88 Kelvin. Right. So we know here there is MCV delta T, so we can get this MCV delta T as 204.52 joule per kilogram. Then Q in here will be combination of heat addition process of constant volume process and a constant pressure process. So we can have this equation Q in is equal to Q23 and Q34. So that can be calculated. That can be calculated by the elimination of the problems formulas. Then we can finally get the Q in as 629.65 joule per kilogram. So calculate the thermal efficiency that you know output by input. So W output can be calculated by Q in minus Q out. So we know the values. Q out value we know, and Q in value you calculate it, and if you substitute, you can get the thermal efficiency of this real cycle as 67.5%. Then what else we have to calculate? The MEP. So you know the formula divided by V1 into here V1 is equal to stands specific volume minus 1 into V1 into 1 minus 1 by R. So we know the values, so we calculate the W net, we know the V1 value, and we know the R value. And if you substitute, we can get the MEP as 522.63 kilopascal. Right. So you know what is Otto cycle, then what is diesel cycle, what are the processes of Otto cycle and diesel cycle, then what is dual cycle, then how the processes of dual cycle will be. Right, then we can compare the Otto cycle, diesel cycle and dual cycle with the parameters. So for the same inlet condition, the same compression ratio and the same heat removal. Just we are taking the parameters inlet condition, the compression ratio and the heat removal here. So if you take these three parameters, then we can compare the efficiency of thermal efficiency of these three processes as the Otto cycle will be greater when compared with the dual cycle, then this will be greater compared with the diesel cycle. So let's look at this comparison. So for same inlet condition, same compression ratio. So here we have R compression ratio. If you want to compare, thermal efficiency of Otto cycle will be more, then followed by thermal efficiency of dual cycle, then followed by thermal efficiency of diesel cycle. So we can get the highest thermal efficiency by Otto cycle, then the least thermal efficiency by diesel cycle. So in between there will be a dual cycle. So we can get that from this PV diagram. Just listen. So this the process 1, 2, 3, 4, 1. This is the Otto cycle process. So this one, so you know Otto cycle, right? So isentropic, constant volume, isentropic, constant volume. Right. This is the Otto cycle. Then second one is dual cycle. So you know isentropic, constant volume, constant pressure, isentropic. Again, constant volume. So why we keeping? Because we have to keep the compression ratio same for the all three processes. Also the inlet processes. Right. So inlet condition. So inlet condition should be same. Also the heat removal also is same. So we are keeping the process like this. Then for diesel cycle, so we have isentropic, then you know constant pressure, isentropic, constant volume. Right. So this is the PV diagram for comparison of all the three processes, all the three cycles with the same inlet condition and same compression ratio and same heat removal. Right. So from that you know the area of this will be give you the work done. So we have to compare. If you calculate the thermal efficiency, the Otto cycle will give you the maximum thermal efficiency for these conditions. Then followed by the dual cycle, then the least performance will be with the diesel cycle. Okay. So this is the order for the same inlet condition, same compression ratio, and the same heat removal. Also, you can compare with this TS diagram. So this 1, 2, this 1, 2, 3A, and this 4. So this is your isentropic, sorry, Otto cycle. Then again 1, 2. Cycle, right? So X and then 3P, then 4. This is your dual cycle. So here we have constant pressure process, then constant volume process, then constant pressure process. So constant volume process is equal than constant pressure process in TS diagram. This you can compare. Then we have a diesel cycle. That you know we want isentropic process, then constant pressure process. So we can get this. So this is approximately equal, right? So constant pressure process, then isentropic process. Again, there is a constant volume process. So this is it, right? So we can compare the PV diagram and DS diagram for the conditions, same inlet condition, the same compression ratio, and the same heat removal. So if you compare these three parameters, you will get the order as thermal efficiency of Otto, followed by thermal efficiency of dual, followed by thermal efficiency of diesel. Then also we can compare the Otto cycle, diesel cycle, dual cycle with the other parameters like the same inlet condition and the same peak pressure. So we have to get the pressure same. We want to get the pressure same and same heat removal. So heat removal also want to be same. So where we can achieve this? So here we can achieve, right? So then heat removal will be here. Isentropic expansion will be here. Same heat removal. Right. Then we can order all the three processes as the diesel will be maximum. Right. So here the diesel will be maximum, followed by the dual, followed by the auto. Right. Just remember the conditions. So here we want to, if you want to have the pressure same, we will get the efficiency as like this. Right. So we can compare this equation for this process. Very much. Right. So move on to this process. This process is constant auto cycle. Then this process constant volume, isentropic, constant pressure, then isentropic, then constant volume. Diesel cycle, and the in between, so isentropic, constant volume, constant pressure, then again isentropic, constant pressure. So this is your dual cycle. So if you compare with this property, we can get the order as diesel greater than dual greater than auto. Just remember the order. Also, we can compare that by TS diagram. So this is your this is your auto. Then this is your diesel. Then this is your dual. Constant volume, then constant pressure. Constant volume, then constant pressure, and again isentropic, then again constant volume. Right. So we can compare for the condition of the same inlet and the same peak pressure and the same heat removal. The order will be thermal efficiency order will be like this: initial followed by dual, followed by auto. Then so again same, right? So the same inlet condition and the same compression ratio and the same heat addition. So first process again same, right? So this is also the first comparison. So same inlet condition and the same compression ratios and the same heat addition. There is heat rejection, but here is heat addition. We want to keep the heat addition as constant. So there we can get the, there we involve the heat addition. We will involve the heat addition here. Right. Heat addition will be here. 2 to 3. 3 dash. So 2 to 3 we will give the heat addition, right? So but in the case the again the thermal efficiency will be in this order: auto followed by dual followed by diesel, right? So we can compare the same inlet condition, the same compression ratio and same heat addition. The order also will be for the same inlet condition, same compression ratio and the same heat rejection. So like this is equal to the first comparison, right? So the auto followed by dual followed by diesel. Right. The first process also heat removal, but the order is like this: auto, dual, diesel. Then auto, dual, diesel. But here we change the condition: heat addition. There heat rejection. Right. right? So, but the PV diagram, PS diagram will change. So we can compare the PV diagram. So this is your first auto cycle. Yes. So this is one function volume and isentropy and function volume. This is your auto cycle, and this is your function isentropy. Then so this is your dual cycle, right? You can take this, right? So this is your constant volume, so isentropic compression. So here we have the auto cycle. Then this is your diesel cycle. Then this will give you a diesel cycle. Constant volume, then constant pressure followed by isentropic process. Then also we can compare the TS diagram. If you compare all the three cycles, we will give you the TS diagram like this. Then we can make the comparison as auto then dual will be greater than diesel. Right. So this is the order. So the question may ask from the comparison. So the condition, based on the condition, we can get the comparison of all the three processes. Right. So with this, we can stop. So we have to see the breakdown cycle in the next class. That is not today, not tomorrow. Tomorrow we have Viva, right? Are you prepared for the Viva presentation? So each and every one will be individually examined on tomorrow, right? So tomorrow we have third and fourth hour. So at that time, each and every one will be individually questioned to get your understanding about the thermodynamics. So up to this, we can ask any questions. So just to try to prepare your assessment one performance was poor. So we are having another assessment. This mark only going to be taken for your assessment 1 mark, right? So tomorrow we have Viva, so just be prepared. Okay, that's it. So if you have any queries, you can ask now, or else you can hang up. Thank you. Have a good day.
Thank you.
question.